So we're excited today to hear a talk by Ove Philipsen, a professor at Goethe University in Frankfurt. For most of you, Ove does not need a introduction, but I will give it for the sake of tradition. Ove received his degree from University of Hamburg, and then went to do a postdoctoral research at University of Oxford, where we, I think, overlapped for just about a month. Then he went to University of Heidelberg, CERN, MIT, Sussex, became a professor in Münster, and now since 2010 he has been a professor of Goethe University in Frankfurt, and also dean of the physics department. Ove is known to the community for his exploration of quantum field theory, quantum chromodynamics, and lattice gauge theory, as well as works in cosmology. He pioneered several approaches to circumvent the notorious sign problem and to help us understand the implication of lattice gauge theory for the phase diagram of quantum chromodynamics at finite density. And today we are excited to learn about the view of Ove on the overall state of that problem, and also about his new results. Please, Ove.
Okay, yeah, thank you very much for the very kind introduction and the invitation and having me in the first place. So originally, I wanted to talk about two topics, interesting developments from the lattice, but I decided to mostly focus on the first one, namely on the hunt for the critical point, the structure in the phase diagram, which is maybe what most of the audience here is most interested in, and then make a whole package and see where we stand on this topic in theory. So there was a major development according to or regarding the chiral phase transition in the massless limit, which is very important in constraining the QCD phase diagram at finite density. And I want to recap how that all hangs together. And I think we made major progress on this question. There needs to be some solidification, but I believe we understand now what the nature of the chiral transition is in the massless limit. And so I will discuss how this all affects the finite density phase diagram. And with that, let's get started. So this everyone is familiar with, and because everyone is so familiar with this picture, and 98% of the talks I see on this topic draw the same kind of phase diagram, I think it is interesting to remind ourselves where this comes from and what are the reasons to expect this. So what makes this so difficult is that on the lattice, obviously, this cannot be simulated at finite density because of a sign problem. That's a very generic thing, also known in condensed matter physics. And unfortunately, it's also non-perturbative physics, of course, in this realm of below GeV scale physics. So that is why, even though the phase diagram is a very fundamental property of QCD, we still do not know from first principles what it looks like. So let me go back in history and recap the motivation for the critical endpoint. That's also a journey in my own personal history, which Misha just indicated. So the reasoning came about at the turn of the last century. And so here is a list of papers that argued for the existence of the QCD chiral phase transition at finite density and a critical endpoint. And I joined MIT in the year 2000, and I was very hooked on this story. So usually the argument goes as follows. You start with two flavors. And when you are in the massless limit, then you have an exact chiral symmetry that is either spontaneously broken or restored, depending on temperature. And if you have an exact symmetry, so an order parameter that's really zero or non-zero on the two different sides of the transition, then this transition needs to be non-analytic. So it can't be a crossover, there has to be a true phase transition. And then at the time, there were several model predictions and which were saying that should be a second order phase transition in the zero density limit. And then there were also model predictions that say you should have, if you go in the finite mu direction, you should have a first order transition. Then in between, there must be a tri-critical point, which will play a crucial role in the sequel. So that's where you join a first order transition and a second order transition. And from such a tri-critical point emanates a so-called wing line. So here you switch now on, so the front plane is the chiral limit, then you switch on non-vanishing UND quark masses. And then from this emanates a wing line. The second order phase transition becomes a crossover because now you have broken chiral symmetry explicitly. And then you remain with this first order transition here that ends in an endpoint. So that was the picture that was consistent with model results and early lattice results. I'll go through that. Of course, if you abandon model predictions and you want to be very rigorous and only work with, say, lattice QCD, then you would have to admit other possibilities. So all we know is that in the chiral limit, so in the massless limit, you need to have a phase transition, but of course it could be all first order, like on the left side. And that is not so nice a scenario because then nothing much follows when you switch on quark masses, except that you have to lose this transition at some point to a crossover, but you don't know when and how much symmetry breaking field it requires. There is also the opposite option where everything could be second order in principle. And in this case, this is a very predictive scenario. Then when you switch on an explicit quark mass, you would lose the second order transition and have a crossover for all the rest. So from this, you can see that even the on-axis, so zero density behavior here on axis, okay, is very important in constraining the possibilities for the QCD phase diagram. And this is where I got started. So a natural starting point is if you can't do finite mu, start with zero mu and worry about what the chiral transition is in the massless limit. Okay, now we're going to extend this to 2+1 flavors. So we are adding a strange quark to the game. And that's what we usually call 2+1 flavors. Strange quark mass is different from the other two. And then the order of the phase transition is usually depicted in this so-called Columbia plot. I have two examples here, and they go back to the seminal paper of Pisarski and Wilczek from 1984. So this Columbia plot has the UND quark mass on the bottom, and this is a schematic. It's not really a plot. It just tells you what is the order of the transition as a function of quark masses, and the strange quark mass is on the y-axis, and they range from 0 to infinity each. Okay, so when all quark masses are infinite, they decouple, they're not dynamical. So that's the upper right corner. You're in the pure gauge theory and you have a deconfinement transition. And the opposite end, everything is massless, then you're in the lower left corner. And the three flavor theory with all quarks degenerate lives on the diagonal of this plot. Okay, and then two-flavor theory. That is when the strange quark mass is infinitely heavy and you have only U and D quark masses. So the two-flavor theory lives on the upper horizontal. And then this plot summarizes what the order of the transition is. The yellow color scheme indicates a first-order transition, and the shaded area here is crossover. And of course, now we know that the physical point, so the physical quark mass configuration, is in the crossover region. Okay, and then in '84, Pisarski-Wilczek predicted more or less two options for this, or two possibilities for this Columbia plot. So what they did is they looked at a linear sigma model in 3D, linear sigma model as a low energy model of the chiral degrees of freedom, the pions and the sigmas, and in 3 dimensions, because at finite temperature you're effectively 3-dimensional. So what they found is, and then they looked at the renormalization group flow in that low energy model, and that determines the order of the phase transition. And their finding was that in 3 flavors or more, so if you have 3 or more chiral flavors, then you always have a first order transition. That's what you see here with the yellow box. And if you have a first order transition, this will extend to some finite quark mass until it goes away. And then the explicit breaking of chiral symmetry is strong enough, so you have a smooth crossover. Now, for 2 flavors, they found the situation was more complicated. Then it depends on the size of the U1 axial anomaly. If the anomaly is restored, you have more chiral symmetry. So instead of the SU2 cross SU2, you have an additional U1. And then they found this can move the chiral transition in the 2-flavor limit also to be first order, like here. Or if the axial anomaly is broken, you would have only O4, that's isomorphic to SU2 left, SU2 right, and then you would have the second order phase transition. And here, this is important, you would have, again, a tricritical point. So at some special value of the strange quark mass, you would then change the chiral transition from second order to first order. And maybe that's worth another explanation. You see the boundary line here. This is drawn in green, and this is my color scheme for a triple line. So if you have a chiral transition in a first order regime, then it's always a triple point. And you can see that down here in a true phase diagram. So here you have temperature and quark mass. And in the chiral limit, if you have a first order transition, then that extends up to some finite quark mass where it ends in an endpoint. So this endpoint here would correspond to somewhere on this blue line. And now, because of chiral symmetry, you can swap the sign of the chiral condensate. And so if you're exactly at this transition point at the critical temperature, you have a 3-state coexistence. You have 3 phases touching each other with psi bar psi, either positive and negative, non-zero, or psi bar psi 0. Okay, and a tricritical point is the endpoint of a 3-state coexistence line, quite generally. And here again, you can also see these 2 second order, so this boundary line here that delimits the first order transition. This is one of these wing lines, like it was discovered or like it was supposed in this finite chemical potential plane. So let's put these 2 things together. And here is one of the driving motivations. So if you start with your 2-flavor chiral model, like here, this is what was suspected in the literature. Now you add a strange quark and you reduce the strange quark mass from infinity, then in models, you see that this tricritical point here starts moving to the left until it hits the axis. And we can now draw this picture in the Columbia plot. So I'm showing you down here this plane, which we just discussed, and then you add a new direction, the chemical potential direction. Now this tricritical point, okay, that's the 2-flavor limit, that's this one here. And then the finding was based on the evidence, model evidence at the time. If you now reduce the strange quark mass, this tricritical point moves down to this point. Okay, so that gives this tricritical point at mu equals 0 its particular relevance. And the question, therefore, was very important on these Columbia plots. Do we have the left scenario or the right scenario? Okay. Now, unfortunately, zero mass quarks are equally impossible to simulate as finite density. So, and the reason is simple. If you have in the quark matrix, it then has a 0 eigenvalue. So then you cannot invert the quark matrix to compute the fermion determinant. And as you approach that limit, your computational cost explodes. So this has limited progress for a long time, of course. And as time progresses, computers get faster. We manage to get closer and closer to the chiral limit, but we never can work in the chiral limit. Okay, so this slide is supposed to summarize what I'm going to show you now in a few steps later on, what was found over the last 30 years. So if you take very coarse lattices and unimproved actions, then you actually find the scenario on the left. I'll show you evidence for this in a bit. Even in the 2-flavor case, you can see that there is some lattice actions which have a first-order phase transition in the chiral limit. And 3-flavor, you see nicely the predicted first-order transition here. Then as you make your lattices finer, so you go towards the continuum limit, what you observe is that this boundary line here marches towards the left, so towards the chiral limit. So this whole first-order region is shrinking. And now you see this is, of course, getting difficult. The question is, if we take the continuum limit, will this line saturate somewhere? Or will it move to this scenario? And this was an open question. And if you look at a fixed lattice spacing, then there were real contradictions between different lattice actions. So one says the left scenario, the other says the right scenario, and there was quite some confusion. Okay, I now want to give you some examples for this. And the first one I start with is we start at the physical point. So we're sitting here. And then people reduced, so they keep the strange quark mass and they reduce the U and D quark mass and walk towards this transition. And the goal is to see whether you cross either into a first-order transition regime, okay, or you approach the chiral limit with an O4 scaling. And the difficulty is in the scenario on the left, if this region is very narrow, then you see you first approach this critical boundary line, which is Z2 exponents, and here you would have O4 exponents. So the question is, can one distinguish that? And here I show you some results from hot QCD on the left. And what you see, the curves of different colors here correspond to different quark masses, which gets reduced. And note here, you can see the general progress. We're now down to being able to simulate 55 MeV pions. That was, of course, completely impossible even 10 years ago. And what you see is that what you see here is the chiral susceptibility, so the mean square fluctuation of the order parameter. And as you approach the chiral limit, your fluctuation gets more violent and you see a peak emerging, but the peak always stays finite, so there is no divergence. In other words, you are still always in a crossover region all the way down to some tiny pion masses. By the way, the solid lines are FRG results. That's another, I think, interesting development. We're seeing a beginning convergence between lattice and functional methods. It's not quite quantitative yet in the chiral limit, but we're getting very close, and this is very useful in this difficult problem. Okay, on the right, you see a similar exercise done with twisted mass Wilson fermions, so quite a different discretization. Here, the quark masses or the pion masses are a bit heavier. They go from heavier to down to the physical scenario. And so both of these collaborations then extrapolate to the chiral limit using this central relation where you employ that you are approaching a critical line, right? In both cases, in either case, we approach a Z2 line. In the other case, we are approaching an O4 line. And now comes the the trick, or not the trick, the difficulty, in my view, this is now my view that I'm giving you here. So both collaborations find that they get an extrapolated chiral critical temperature, okay, which they can determine very accurately. Note the small error bars, and the small errors include switching between the critical exponents between Z2 and O4, okay? And of course, that's not so surprising if you want to calculate these, because they're in the exponent, you would need exponential accuracy. So this is very difficult. And what I conclude from this is, if I cannot distinguish in the critical temperature between my different sets of exponents, then I cannot distinguish what the order is of the transition. This is very, very difficult. And then another issue is, this is very new. There is a new paper published by the FRG crowd just a couple of weeks ago, and they are asking, in this O4 scenario, how big is the scaling window? So how close do I have to get to this line before I can see the scaling window? And what they conclude is that your pion has to be within 5 MeV of the chiral limit. So that is, of course, very, very small, and it highlights the difficulties in doing this on the lattice. This is not within reach at the moment. Okay. So this was on a physical point approaching the chiral limit. Now let's go to the 3 degenerate flavor situation. And I am showing you an example here from our Japanese colleagues. So they find the boundary to the first order region here in the 3 flavor degenerate case. Then you have a quark mass configuration, and then you calculate what the pion mass would be for this bare quark mass, okay? And in this way, you can compare with different discretizations. So this is order A improved Wilson fermions. And what you see here is the value of the pion mass computed on this boundary point as a function of lattice spacing. So you see here 1, 2, 3, 4 different lattice spacings. In fact, they have a 5th one, which is not on the plot. And now you can see that there is a humongous cutoff effect. So if you look at the numbers here, you have M pion over T is 4 on the coarsest lattice. And here we're down to 2. So you have half the size of this first order region if you measure it in units of pion mass. This is an enormous cutoff effect. And this is on lattices which are already, they're not so coarse anymore. And this is an order A improved Wilson action. So this was very confusing. And then if you try to take a continuum limit, you see there are 3 different extrapolations, and they give you either a large first order region or none at all. And in fact, they have only included 2 or 3 points here. So no controlled continuum extrapolation is possible at the moment. The picture is the same if you take staggered quarks instead. So here is some data from Philippe de Forcon and Massimo Delia from a few years ago, and they looked at, this is 4 flavor staggered fermions, 4 flavors because you don't need routing, 3 flavors, and you see the same qualitative behavior as you make the lattice finer. Your pion mass evaluated on this boundary again shrinks drastically. So far, so good. But what is again very discomforting is if you look at the absolute scale. So let's take the 3 flavor situation here on the n tau, what is it here? N tau 6 lattice. Okay, we have an m pi over t, which is 1. If you compare this with the Wilson fermions, the 6 n tau 6 is this T equals 4. So we have almost a factor of 4 difference between 2 different lattice discretizations. And that is, of course, also very, very worrisome. Okay, so this is where we started to join this with a different strategy. And our strategy is we're looking not so much for these scaling relations, that's exponentially hard. I think we have no chance to do that. What we now want to do is figure out where is this dry critical point? Does that exist or not? Because that will distinguish between the two scenarios that we discussed. In order to do this, we change our variables. So we change from a 2+1 flavor theory to a theory with NF degenerate flavors. And then instead of varying the strange quark mass, right, the strange quark mass interpolates between, here we have 3 degenerate chiral flavors, here we have 2 degenerate chiral flavors. So what we do instead is we simply write our quark determinant to the nth power, like usual, and then we vary our NF continuously rather than in integers. And that is very beneficial. Now you can translate this Columbia plot to these new variables. So here I have now quark mass. Okay, I have only one of them. All quarks have the same mass. And on the bottom, I plot instead NF. And now I'm gaining 2 things. Number one is I'm guaranteed to have a tri-critical point because if I reduce my NF to say 1, at one flavor, there is no chiral transition anymore. So any first order chiral transition, which we have explicitly observed, I've shown you the examples previously, must go away in a tri-critical point. Okay, and the only question is, where is this tri-critical point? And the second benefit is the strategy is now I'm starting from a point where I know I have a first order transition. I sit on the Z2 boundary and then follow it towards smaller NF. And then I don't have to guess what the exponents are. I know the exponents because this wing line is guaranteed to enter the tri-critical point with tri-critical exponents. These are mean field exponents because the upper critical dimension for tri-criticality is 3. And so I know how I enter this tri-critical point. So this is the strategy. And just for illustration, so here is the second order scenario, right? That would put my tri-critical point between 2 and 3 flavors somewhere. And the good thing is now if I have this scenario, then this will also have a tri-critical point. In this case, it will be somewhere between 1 and 2 flavors. So I have the same situation. I don't have to make any assumptions. I'm just following this line, and then I'm looking where does it end up on the axis. So this is the strategy with one complication. Since we are on the lattice, we have one extra direction in this plot. So you have to now imagine there is a third axis with lattice spacing, and then this tri-critical point here is becoming a tri-critical line as a function of lattice spacing. Okay, a quick word on how we do this. So the methodology is very standard. We do finite size scaling of generalized cumulants of our order parameter. So the order parameter is psi bar psi. Then you measure the fluctuations around its average, and you take the nth power. These are the moments. And then these ratios are the generalized cumulants. And they basically tell you about the finite size behavior of the distribution of the order parameter, from which you can infer the order of the phase transition. This is very safe and standard in condensed matter physics, but it's also very statistics hungry. And so 2 things. First, the general strategy. We're doing this with staggered fermions, and we have 4 parameters, 4 bare parameters. So we're simply trying to distinguish in our bare parameter space the regions with a crossover, the regions with the first order transition, and the separating boundary, which is a second order transition. So the parameter space is 4-dimensional. Okay, then you first found the phase boundary, so chiral condensate large or small, And we do that by the criterion is vanishing third moment. That is basically you have the same weight on in both bases. That's what this criterion is. Then you have one constraint, you're reduced to a 3D manifold. Then that 3D manifold falls into a section with crossovers and a section with first order transitions. And the boundary then is a surface, and that is a surface in the 3D Ising universality class. And that will separate the two sections. Okay, and this is determined by the fourth moment, or the cumulant, it's called, and it's finite size scaling. So I show an example here. You see the fourth moment as a function of quark mass, and you see three different volumes. And in the infinite volume limit, this becomes a step function. And for different finite volumes, the intersection point here will tell you this is the critical point. So this quark mass will be precisely this blue boundary line that we are looking at, this Z2 boundary separating first order from crossover transitions. Now, the important thing, I don't want to be too technical, but what you'll see in the results section is only these intersection points. Okay, now you can see here on this plot, we see something like 10 or 12 data points. And these 10 or 12 data points already each represent 4 different parameter sets, okay, because of this strategy. So here is the abbreviation. What do? We first search the phase boundary. So here you see this skewness plotted with different data points. Every parameter set, we have 4 different Monte Carlo chains. So we can monitor we can evaluate what the autocorrelation length is, and we can really see that we're independent of our Monte Carlo seed and so on. And only if 4 chains agree, we throw them together, and then we have more statistics. So first you find the zero crossing of this, that gives you where the phase boundary is. Then you evaluate the cumulant on this zero crossing. And then you have to find the minimum. And then you have to repeat this for different masses. And every mass, you have to repeat the whole exercise on 3 different volumes, okay? So what you see on this plot is already a set of something like 40 different parameter sets that you have to simulate. And of course, each of them needs enough statistics. So this is really a tremendous numerical effort, which we have mostly run on AMD GPU clusters at either GSI or Goethe University in Frankfurt. Okay, on to the results. So here is exactly the numerical manifestation now of this Columbia plot. So I'm plotting mass, quark mass, bare quark mass in units of t as a function of NF. And these are all these second order boundaries that we have managed to map out as a function of NF. And the 3 different colors correspond to 3 different n tau's or 3 different lattice spacings. Small n tau is coarse, large n tau is fine. So what you see here is what we knew already. Let's start with the n tau 4 lattice. We see on the left, this is the larger quark mass region. You have crossover transitions, and below you have first order transitions. And we see that if we add more flavors of massless quarks, this first order transition gets stronger, as we had naively expected. And we also see that the first order, or that this first order transition region appears, okay, and you can extrapolate this to a tricritical point. And then below, there is no first order transition anymore. Here you would have a tricritical endpoint, and then second order or no transition. Okay, in order to see this tricriticality, you have to zoom in because we have a remarkably linear behavior here. So let's zoom in on this n tau 4 data, and I'm rescaling my axis. So this is now the correct scaling field. And you see that indeed on the smallest mass points, we're just about reaching the leading order scaling regime. That's very difficult. And here you see the second order modification. So I've expanded you can usually fit this by a Taylor expansion in terms of the scaling variable instead of an ordinary polynomial, and that allows you to extrapolate, and the tri-critical point then would be here. And this is what I've told you. So this is unimproved staggered quarks on a coarse lattice. Okay, tri-critical point is between 1 and 2. And what you conclude is that on this lattice, you have a first order scenario or this situation. Okay. But now this is, of course, a very coarse lattice. And now if you go to n tau 6, you see that this changes. And now our intersection point here, the tri-critical one, is between 2 and 3. And this now is a changed situation. So this lattice is finer, and it corresponds to this situation. That's NF between 2 and 3, means we have a tri-critical strange Quark mass somewhere. And now comes the shock. This is something that I didn't expect. If you go now to the next final lattice in tau 8, you see not only does this first order region keep shrinking with no tendency to converge to a continuum limit, also you see that this tri-critical point moves from somewhere between 1 and 2, and then we have 2 and 3, and then it keeps moving to the right. And that's a very interesting phenomenon. Now what I'm going to show you next is always the same data point, but I'm plotting them in different variable pairings. Remember, the chiral critical surface is a 2D object, and I'm projecting this onto 2 different variable pairings. It's always the same surface, but we can learn something by a different perspective. So in particular, we can verify this is now bare lattice gauge coupling and quark mass. That's not particularly instructive, but it serves very well to verify that you have a fantastic next to leading order description of the data in the scaling variable. And if you try to fit this by an ordinary polynomial, it's much worse. And by the way, these boundary points are parameterized internally by the different values of NF. Okay. This is more instructive. So again, the same boundary. Now I fix the NF. So we're back to integer NF, the physical situation. Again, always small quark mass is first order region, above is crossover region. And you see again, you're close to leading order tri-critical scaling, and you have tri-critical points here. And that means that your first order transition region terminates. And in this case, we're not guaranteed a tri-critical point for a fixed NF. Okay, you don't know where it is. So you can try to fit this boundary line such that it would go through the origin. And that is what it has to do if you want to have a first order transition that is connected to the continuum limit, which is at A0. Okay, so that's the origin of this plot. And what you find is that these points are no way compatible with any polynomial that goes through the origins unless you would admit both positive and negative masses at the same time. And this has now a very clear interpretation. What this tells you is that this first order region is not continuously connected to the continuum limit. And so these are the 2 possible scenarios. If you want to have a first order chiral transition in the continuum limit, then your lines of constant physics, where you keep the mass spectrum and the temperature and so on constant, they have to, they all walk into the continuum limit. You have different trajectories. Okay, but the continuum limit invariably is in the origin of this plot. And if you have a tri-critical point on this plot, so tri-critical AT means there is a tri-critical n tau, then it means whatever you do, eventually your continuum limit will leave this first order region and approach from the crossover side, and then you have an isolated second order chiral transition here. So this is our conclusion, and the interesting part is that this is the situation even if you increase the flavors to 4, 5, 6, 7 is the last one where we have clear evidence for a tri-critical point here. Okay, now let's go back to the Wilson quarks. Here is the same data I showed you before. And what we now did in our paper, so this appeared a year before our analysis, and now we just take the same data points and rescale them, because if you have a tricritical point, then an ordinary polynomial fit would not be appropriate. And this is what you see on the right side. This is the exact same data points. And what we do is simply we rescale them and use the proportionality of the square of the pion mass to the quark mass. And then you see that you will now get different leading and subleading order tricritical scaling fits, and they fit snugly on the line. You see there are 3 even in the leading order regime. So this satisfies fantastic tricritical scaling. The chi-squared is better than those in original fits from the paper. So this is entirely consistent with the staggered result. And you would conclude also that for 3 flavors of degenerate Wilson quarks, your first order region that you observe stops somewhere, okay? And then beyond that, you're always only having a second order chiral transition. And here you can see again the difference of the cutoff effects in the staggered situation. So 3 flavor is the red points. They are not finished, but you can see we're definitely down here at n tau of 10, say. So if you have an n tau larger than 10, you would get the right result with staggered quarks. If you take Wilson quarks, then you come down here at something like 20. And I imagine the explanation for that is, so first of all, cutoff effects are, of course, action-specific. And secondly, Wilson quarks don't have chiral symmetry, whereas staggered quarks have at least a subgroup of that still realized. So that's a natural explanation. Okay. So yeah, maybe one more remark. You can plot the intersection points here. So this is the lattice chiral limit. And you can plot these. This is what I've done here as a function of NF and 1 over n tau, or AT. And the question is, so do we have a tricritical point in the continuum? So far, we haven't seen that. You see, as we increase NF, these lines walk to the left, but the continuum limit is here. And the question is there any NF where we have a tricritical point in the continuum? And I do not know the answer. This is just a teaser for the future. So here is the chiral transition, all quarks massless as a function of NF. People have also looked at this with FRG. And then the transition temperature at some point goes to 0, and at some large number of flavors, you approach the so-called conformal point, or the conformal window, where you stop having a chiral transition at all. And so we have checked everything to the left of 7 flavors, not to the what is to the right of 7 flavors, or at larger numbers of flavors. But I think it's quite possible that we have only second order transitions all the way. Okay, so let's go back to our physics question. The conclusion is now that the Columbia plot in the continuum would look like this. We have not found a tricritical strange quark mass, okay, no tricritical point below NF7. And that means that you have a second order transition all the way here for any value of the strange quark mass, all the way to the 3 flavor chiral limit. And what we don't know is what is the universality class of that. So the largest chiral symmetry would be U3 cross U3. And that's, of course, remains to be determined by different methods. What are the sets of exponents for such a large universality class? What about Pisarski-Wilczek? Immediately, Rob was suspecting the epsilon expansion. I don't think this is the problem. The Pisarski-Wilczek conclusions were confirmed with very different methods, by lattice simulations of 3D sigma models, by high-order perturbative investigations in fixed dimensions. It looks now, since then, that in fact it's the model itself which is the problem. So there is no reason to stop at a linear sigma model in 3 dimensions. You can have, for example, phi to the 6th term, which is even renormalizable in 3D. But if you consider this as a Ginzburg-Landau-Wilson theory for your order parameter, you don't need to to be renormalizable either, so you can have even higher powers. And there are two investigations that remove the contradiction. So there was one paper that does an FRG study of a phi to the 6 model, including TOF term. And then they find an additional infrared stable fixed point as a candidate for a second order phase transition. And there is also an interesting work using numerical conformal bootstrap methods. And that says you can have indeed for a U3 cross U3 universality class an infrared stable fixed point. Of course, these two investigations don't prove that QCD has such a fixed point, but they remove the contradiction and they tell you we have to look at different models. In the meantime, we have also progressed in Frankfurt, and what I show you here is the same, these 3 points. This is, again, this AM versus AT plot for 6 flavors. And what is new is now we have an n-tau 10 point, and it's very satisfactory. That sits exactly on the predicted curve that we published 2 years ago. So no surprises with final lattices. This seems to be stable. What else has happened in the meantime? Also, hot QCD has taken to this problem, and they sit on the 3-flavor diagonal here, and then they reduce their quark masses, and they have now beaten this down to 45 MeV pion mass. Okay, and they find no sign of a first order phase transition. So this is deep in the first order region where the old order A improved Wilson fermions would have seen a first order transition. So again, you see the apparent contradiction, which is only resolved in this picture which you see here. And finally, there is also work in progress by a Japanese group, and they are using domain wall fermions. They are sitting at also 3 flavors, but physical points, so it's not that light yet. But the good thing is they have appropriate chiral symmetry also on the lattice, and they also so far only see crossover behavior. So everything is consistent. Okay, let's move on to see how this picture changes with chemical potential. And this is something you may, or several of you may remember. So this is how I got started in this business. Here is again our Columbia plot with chemical potential, but I'm plotting chemical potential squared. So then I have real and imaginary chemical potential. And imaginary chemical potential can be simulated without sign problem. That's what I have done for many years. And maybe you remember this old result with Philipsen, where we followed how this boundary, this Z2 boundary behaves. Okay, and this is what I'm showing you here. There's a very well confirmed with a bunch of references, but coarse lattices. And what you see is that the first order region widens as you go to imaginary chemical potential, and it gets a bit narrower as you go to real chemical potential. So what we've done now in the last 2 years here in Frankfurt is we have repeated our study that I was just reporting to you, this Columbia plot study, except we fix now an imaginary chemical potential. Okay, so this is what I've been talking about so far, and we only have this second order line here. And now we go downstairs to imaginary chemical potential, and I look at the Columbia plot in some fixed plane at this value of chemical potential. And we do again the same exercise. I can repeat all the plots. They look all the same. And here is just one example. Here is again our scaling field, the quark mass. And again, you see that the first order region entirely goes away. So it's the same situation. And this entire boundary here just moves as a function of lattice spacing to the wall, to the left wall, until it looks like that. And I have a couple more. So this will come out in, I guess, yeah, before Christmas, definitely. This is almost finished. We're writing the draft. And there is more to back this up. Already a year ago, and Massimo Delia with collaborators has done this already a bit earlier. They have gone all the way down to the bottom plane here. This is the boundary to the next center symmetry sector at imaginary chemical potential. And hot QCD together with us, we have started at the physical point and approached the chiral limit in two different directions. And this is now different discretizations. In one case, Stout-smeared like Wuppertal, in the other case, HISC. And you see no sign of a phase transition. So this also speaks in favor of this picture. And finally, there has been a Dyson-Schwinger equation study. Also, that's brand new, published about a few weeks ago. And they look at the area around mu equals 0, plus minus 30 MeV in chemical potential, and they confirm in their truncation that there is only a second order line for any strange quark mass here in the 0 mu plane, and that is stable under variations of plus minus 30 MeV is what they say. What's nice about this is that it shows that this chiral critical surface is analytic around mu equals 0. Okay, let's come back to the beginning of that story. 20 years ago or so. What does that imply? So what that implies, this is the left picture is now where we stand if we take these results at face value. So what's missing is, of course, the continuation to larger chemical potential, unfortunately. And that means nothing is ruled out. The critical point is not ruled out, but the situation has changed to what we expected. You need an additional critical surface here, an additional blue structure somewhere, which has to hit the wall, and it's not connected to the 0 mu situation. So in other words, what we discussed initially 20 years ago, all these models that predicted a connection between a critical endpoint at finite mu and at 0 mu, parameterized by the strange quark mass, all such models are definitely ruled out now. So that doesn't make things easier, but it narrows down the possibilities, and we know better where to look now. Okay, let me translate this into a couple of bounds. So from the temperatures that we know now, so hot QCD has also computed the critical temperature in the chiral limit, right? So we know what TC is here, we know what TPC is here. And from this general picture, which I quoted in the beginning, it implies an ordering of these different temperatures. The critical endpoint temperature has to be lower than the TC here. And from this alone, together with the curvature of the crossover, we can put a bound that the critical endpoint must be beyond something like 485 MeV for its temperature to be below this TC. That's a minimal requirement, very conservative. And I'm skipping two other in-between temperatures. Okay, so probably this is a rather conservative bound. Then I should probably speed up. I must have been very slow. You can also go back to the physical point. This is already a bit older, but I want to recall it here because it fits the picture. Another method to learn something at the physical point about the phase transition was to look at Taylor expansions, right, of the pressure as a function of mu b over t. And the coefficients are the baryon number fluctuations, which are also experimentally accessible. And the coefficients you can also calculate on the lattice. Now, let me skip all the technical details and just recap. There has been a number of years ago a cluster expansion model of these lattice results, where you feed in the leading two coefficients from the lattice. And then you model the higher ones by a recursion relation. That's not QCD, that's really a modeling, but it's a very interesting game. And you require that at large temperature, these coefficients all fit to perturbative results. And then you can play funny games. You basically predict with this cluster expansion model where you have Taylor coefficients to all orders, okay, this is consistent with all known lattice results at zero and imaginary chemical potential. So you describe, for example, this cumulant ratio, the famous one. Quantitatively, you describe the non-monotonic chi-8. You can translate the hot QCD results to the Wuppertal-Budapest results, which is only possible if both lattice results and the model are not too far from the truth. And so this is all an interesting game. And now you can really play this. You can ask the question, what is the radius of convergence of this expansion? Because we have all coefficients. And then you find that the nearest singularity in the complex plane is a transition in the imaginary mu direction. That is precisely this Robert-Schweiss transition, which is known, but nothing is seen before that. And this is quite interesting because the data you feed in are real chemical potentials. So this is quite an achievement. And of course, this model is not QCD, but what we conclude from here is that the available QCD data have nothing that enforce a singular point within this radius. Okay, then here is some hot QCD data. They have looked for Lee-Yang zeros as a function of mu and t. Lee-Yang zeros, if they are on real parameter values, signal a true phase transition, and otherwise they move into the complex plane. And here you see imaginary part of chemical potential versus real part of chemical potential. And the shaded area is where you have Lee-Yang zeros. So you see they are in the complex plane, which means you don't have a non-analytic phase transition. And now it's up to you. One can, of course, hope or see that these might continue to squeeze the real axis if temperature is further decreased and mu is further increased. This is a possibility. But as of available, so nothing is excluded, but the available data don't see any sign of a true non-analyticity. And finally, here is updated reweighting from the Wuppertal Budapest group. They have tremendously improved their reweighting technique, basically abolishing the overlap problem. And this plot is very nice. You see the chiral condensate as a function of negative and positive mu squared like before. And you can test this reweighting, which is the black data points versus analytic continuation with imaginary mu. And you can compare fugacity expansion to Taylor expansion mu over t. Everything is consistent and everything is completely smooth in the crossover region up to about 2.5 in mu b over t. So here is the summary of constraints on from the lattice. This is what I have just gone through, and you see the constraint is not really great yet, but it's beginning to emerge. So I think we're controlled. There is nothing within mu b over t about 3, and if we look at the lattice alone, I would say we still have these two possibilities for the phase diagram and its relation to the chiral limit. Now, all of this is consistent with DSE and FRG, and they predict a critical endpoint at quite larger mu b over t. So this is the current estimate, and that would be a mu b over t that's almost 6. So that's a way to go still. The interesting question, of course, is maybe we can find other ways of checking how reliable these truncations are. That would be quite interesting. Okay, so I just about managed. Here are my conclusions. To me, there was a big surprise, namely the chiral transition at 0 density is second order for 2 and 3 flavors of massless quarks. And so far, everything, there are no contradictions, everything is consistent. We'll see what happens in the future, but unless, well, both Wilson and staggered discretizations are fundamentally sick, I, at the moment, don't see how one can avoid this conclusion. So the next step was, that's in the making. Imaginary chemical potential doesn't seem to have an effect on the order of the chiral transition. So it doesn't get weaker or stronger. It doesn't get shifted in its position. It's completely unaffected by Emac mu. And that rules out a whole bunch of low energy effective models. And I take from this whole thing one important lesson, which I think I would like to pass on to you. We have seen incredibly strong cutoff effects on the phase diagram. What does that imply? The cutoff lives in the UV. That's UV scale. So what we can conclude from this is that if you want to determine what the phase diagram of a theory is, you have to have a correct representation of its UV sector as well as of its infrared sector. So I think low energy models can be quite deceiving. You can have low energy models belonging to different complete theories with quite different phase diagrams. So unfortunately, I think we will have to keep to bother with QCD. Thank you very much.
All right, thank you very much for this. You covered quite a lot of ground. So I'm sure there will be a lot of questions. Rob Pisarski wants to ask a question.
Hi, Ove. It was a beautiful summary of your very interesting work. I just wanted to comment, could you go back to the slide with Pisarski-Wilczek?
Yeah.
You didn't number them, so I don't know how to...
Yeah, sorry, I keep always forgetting to number.
Yeah. So in the epsilon expansion, without the axial anomaly, UN cross UN is predicted to be fluctuation induced or pseudo-critical for NF bigger than square root of 2.
Mm-hmm.
So first order for 2 and 3 flavors. And you said now the references you cite are rather old, except for the last one by Kussfoss and Stergiu, who find an infrared stable fixed point.
Mm-hmm.
And I put in the chat results from the it was first done by Nakayama and Otsuki for 2 flavors, and then the second work confirms their work, and Kussfoss and Stergiu find also a second order transition. So there is a contradiction. Leading order in epsilon appears to be wrong according to the conformal bootstrap. You said there was no contradiction.
I would say I'm not sure about that. If you would repeat the epsilon expansion with a phi 6 term included,
it won't matter. It's an irrelevant marginal operator.
It doesn't matter.
Okay.
I also wanted to ask. Wait, I wanted to ask one question though, because I just wanted to comment on that. Yeah. Okay. Could you comment on your work in 2016 with Brandt and Harvey Meyer and others for 2 flavors, where you find that I think is very similar, because you find there that the eta gets light near TC, right? Like 1/10 of its mass at 0 temperature.
Yeah. So okay.
So the approximate restoration of axial U1, because that's really the question, the approximate restoration of axial U1.
So Rob is referring to a paper from a few years ago where we looked at the strength of the U1 axial in order A improved Wilson fermions, and the conclusion was the opposite to what I've just been saying. Namely, the conclusion was that it restores and you find a first order phase transition. Okay, and now you see the largest n tau that we had in that work was n tau 16, which is still, I think, record for Wilson fermions. However, this is now here why I went back to this page. If So you can reconcile both of these things. You see this tricritical point here is at something, now the intercept here wiggles a little bit, about 20, and tau 20 or 24. And so that means that plot would say you only get the correct universality of the chiral transition with Wilson quarks, order A improved, if your n tau is larger than 24, say. And that was not the case in that study with Harvey Meyer and Bastian Brandt. So again, there is, I mean, whether this is the anomaly or whatever causes this I cannot say. That's sort of numerics, but there is no contradiction. Could have been that simply the lattice was not fine enough.
Uwe, Thomas has just made a comment in the chat which echoes what I was trying to say. Thomas, do you want to comment on that yourself?
Yeah, I don't have anything clever to say, and I have to leave in 2 minutes to teach. But yeah, I'm not sure. I mean, you somehow throw out the words "the anomaly is restored." I don't think I don't know what that can possibly mean. It's it's a quantum effect proportional to h bar. It can't possibly go to 0. What you can somehow check is whether there may be certain effects of the anomaly. Like, I'm not even sure that, say, a reduction of the eta prime mass means the anomaly is restored. It just means that a certain effect of the anomaly is no longer visible. But in principle, this cubic term, you can never make it go away. It's always there.
That's sure,
certain effects of it are suppressed.
Yeah.
And so, since you warned about the use of low energy effective models, I think in that spirit, it's very dangerous to use a low energy effective model and arbitrarily set some coefficient to 0 when that is not required by any symmetry that we know of.
Right. So what people do on the lattice is usually they take some criterion. In our case, I think it was screening mass degeneracy. So you look for the whatever is the screening mass corresponding to the eta prime and so on, and look when they become degenerate. And as you say, that's of course also a quantitative question. What people wanted to see is whether you have more or less effective symmetry at work, essentially. So, but as I was saying, so that is a very specific question, and it doesn't contradict this finding, which is the same discretization. So that's really a one-on-one comparison. But it would say that you have to have larger than 20 n tau to see the correct behavior in 3-flavor QCD with actually, I think this was 2-flavor that Rob was asking, but anyway. Yeah.
Yeah, but for the argument to work, or rather for the conclusions of Pisarsky-Wilczek to be to work, approximate restoration is not enough. It has to be exact, right? And there is no such. You cannot restore something which didn't exist. That's what I'm. The way I do it, you can restore spontaneously broken symmetry because there is a symmetry, right? But anomaly means there is no symmetry.
Right.
To start with, there's nothing to restore. So it might emerge in the infrared, but it's a completely different story, right? It cannot. If there is a relevant operator like phi cubed in 3-flavor theory, its coefficient cannot be 0 because some symmetry is restored because it's a relevant operator. So I still don't understand how this argument of Pisarsky-Wilczek could be circumvented. And even though, for example, the argument that for n f equals 3, the transition has to be first order, cannot be second order because there is no critical well, there is no conformal theory at that point.
No, but that is not correct. I mean, that's exactly what. So here, the last reference says
Yeah,
conformal theory at that point.
conformal bootstrap is not an exact science, right? It allows you to find some evidence for such. For example, it allows you to calculate critical indices, which just happen to coincide. It doesn't prove that there is a infrared stable fixed point. It's also a truncation. It's not an exact science. You cannot conclude from that there is such a universality. If there was such a universality class, then Gaufter and Zanilovich should have seen it, right? They have.
No. I disagree with that because you have a different realization of the symmetry. That's again the UV versus IR sector. So I think what the conformal bootstrap shows is that you can have a conformal theory with that global symmetry. And that's it. Whether QCD reduces to that or not is a different story. That it doesn't prove. I agree. But I think if I understood correctly what conformal bootstrap does, I thought it is an existence check if you have the possibility of an infrared stable fixed point with that symmetry. And I thought that is in the affirmative. And you see, this is much more general because they make no assumption about what the Lagrangian is. So you don't have to argue what terms to include, what, or not, and how the coefficients are tuned. It's much more general than that. So it just says such a thing exists. It doesn't say if it is related to QCD. But so the point of this slide is, I think, so epsilon expansion may be one issue, and but I think it's the issue is you can't specify a specific Lagrangian of an effective low energy theory and claim this is QCD in the infrared unless you have integrated out all scales exactly.
I'm not sure how that works. I still don't see how what exactly is wrong with the argument of Pisarsky-Wilczek. That's what I'm trying to say. So I understand the evidence to the contrary, but that evidence could be also questioned. So until we see exactly what is wrong and why this argument doesn't work, why specifically for an f equals 3, where you don't even need epsilon expansion to see that the transition has to be first order. How this argument goes wrong, it would be interesting to understand, I would say. I wouldn't say that finding an evidence, especially for conformal bootstrap, it's an excellent method to determine the critical exponent to a high precision, but I'm not sure you can just rely on it in this way.
Yeah, I certainly agree. It's not solving our QCD problem.
Yeah. Okay. Any other questions? So then I have a question, if there is still time.
Yes.
Rob also put something in the chat box, Misha.
Rob wrote something. Should I read it, or Rob, do you want to?
I think people can read it. I just, I have to say, I think Goethe's work is very profound. I think it raises very interesting questions. Clearly, we're still sorting it out, but I've never been so happy to be wrong. So the epsilon expansion is wrong. I mean, Anna Hassenfratz has talked about using 4 flavors. And at this point, I would expect she'd find a second order transition and conformal bootstrap is right. But clearly, conformal bootstrap is not definitive. Anyway, I'll let, I'm sure Derek has something interesting to say.
Not really. I just wanted to get some clarity. So I mean, so the definite statement is this lower corner of the phase diagram is certainly less than 45 MeV, right? If you look at 3 flavors, right? I mean, that seems to be agreed upon by everybody. That it's, if it exists, this lowest corner of the Columbia plot, right? It is less than 45 MeV, right?
That is if the lattice methods are correct.
Yes.
But it's many. I mean, this was, you know, the hot QCD and, you know, extrapolating at the three flavors points and carefully, you know, so, and they find 45 MeV, less than 45, right? I mean, that's what I took, right?
Yeah, but extrapolating, as Uwe also pointed out, extrapolating to chiral limit is a very tricky business.
Yeah, but so
I understand. So, but still, okay. I mean, and now, so, and then I had a similar question to Rob, like, what about 4 flavors? Like, according to you, 4 flavors also is just completely, like, what would it be then? U4 cross U4? I mean, I have no idea. Right?
Let me put it this way. The symmetry of the theory which is being simulated with staggered fermion is completely different from the symmetry of QCD. And then when you take the quartic root of the determinant and raise it to power 3, it raises all kind of questions about whether it's a legitimate quantum field theory, right?
That's interesting. So then in that sense, the other fermions, like this domain wall fermions, super important, right?
that's right. So I mean, this is why also in the first paper we immediately included the Wilson results, because then you don't have, there is no routing there involved at all. Okay.
Yeah,
so,
but fermions are also notoriously problematic, right? With all these massive pions, and you yourself said that ultraviolet is very important.
absolutely, yeah.
So
yeah, but you see, the interesting thing is, so I completely agree, and this is of course will remain a problem with lattice is never a proof, right? But if you look at essentially at the lattice spacings that are involved in this game, also in particular on the Wilson, for example, then you have to admit, or you will see that these lattices are really beginning to be quite fine. I mean, this is competitive stuff in vacuum QCD even. And so
now, you start with a theory with a different global symmetry, right?
Yes, that's right, and essentially this is exactly what the point of the result is. It shows you that you have to first take the continuum limit and then the chiral limit. If you do it the other way around, you end up in the wrong universality class. So this just confirms exactly what you say. But that is somehow the if you like, the that causes the effect.
Well, according to a comment by maybe Jabosh, maybe you can you want to say something?
Yeah, I just wanted to say that I'm often worried about statements that lattice is fine enough because this number is high, like 10, 16. So the action will not be better because it's more expensive. And if we can hardly pay for it, doesn't mean that it's good. If you look at what, you know very well what pace breaking is and how slowly Wilson fermions recover the chiral symmetry. These numbers are known, right? The pace breaking that staggered fermions have are way higher than the pion masses. So I don't know. This 16 or even 32, I don't think it's fine. These are very close lattices still. I can completely agree with everything Uwe said. but this point, right? These are not fine lattices.
Yeah. No, but if you take, I will say, so one thing that's also not a proof, but if you look at the lattice spacing, then you can find umpteen quantities which are well described, say spectrum, with improved staggered or Wilson fermions at comparable lattice spacings, but not this question of what the order of the phase transition is.
Yeah, because a chiral limit is involved. I think that's the way I understand.
But chiral symmetry is also involved in the spectrum.
That is broken, right? That's the breaking of the chiral symmetry. It's not.
Yeah, but the spontaneous one and not the explicit one by lattice action. So the question is, why would, or something like the eta prime and so on and so forth. So the question is, why is this cutoff effect so tremendously large in this particular question? And can we?
I suspect it may have to do with anomaly.
Yeah, and so then indeed I think the resolution will be, and that's on the way, but of course this will take some years to do all of this with overlap or domain wall.
Yeah. Yeah, it's certainly an interesting question. Yeah, it's just I'm not convinced that that we understood what is wrong with Pisarsky-Wilczek argument and whether chiral limit and continuum limit taken simultaneously on the lattice is reliable at this point in time.
That's exactly the message. It's not you first have to take the continuum limit, then the chiral limit. All I'm saying is, so if I follow this procedure with all actions where I have results, there is zero evidence for a non-analytic phase transition.
Yeah, as is often said, the absence of evidence is not absence. So I also picked up. Does anybody else want to ask a question? I don't want to. Okay. So also for as a matter of clarification, I just wanted to understand. So you mentioned somewhere towards the beginning of the talk that FRG group who's doing FRG claims that you need to go to mass of the pine less than 5 MeV in order to see O4 scaling. Does this contradict the statements from lattice groups which claim that they see O4 scaling? I don't think the lattice groups which say this go to such low quark, such low pine masses.
No, of course not. So now it depends who you are asking. So that's what I mentioned. These, as you can see, even in the right figure. So these groups announce they are consistent with O4 scaling. But I had, long before this FRG paper, always a problem with this, because if you, I mean, this is what you can see on the right figure. Sorry, I have to shift. Okay, on the right figure here, you can see two extrapolations. One is with O4 scaling and some based on some observable, and the dashed lines are with Z2. Okay, now you can see. Note these dashed lines here, they bend downwards, and you would have so here you could have a first order region going all the way out to something like 90 MeV pions.
Yeah.
Okay? And this is equally consistent with the data as the O4 scaling. Mm-hmm. So the question is what you want. If you're happy with is consistent with, then okay, that's a true statement, but I think that's a bit lame for a first principles approach, right? When do I believe that I have scaling? That's when I can calculate these exponents, and if we want to apply experimental standards, then I should calculate these exponents with 5 sigma significance to the between the two, okay? And there's no way they can do that.
Mm-hmm. So I say
and essentially what the FRG people now say, and they had, so I know this argument because they've been fighting with Fritjof for a while. So if you look at this combination, you have a combination 1 over beta delta, and that is not too far from 1. You can see this is, you know, a fairly structureless curve, okay? And what they do is they take 2 different definitions of this exponent delta in the FRG paper, and they look, when can I self-consistently get the same value in both ways of determining this? And then they have said this before, but they have said it for models. They see the same thing in, say, Quark meson models and things like that with a chiral transition. And now so I haven't read or understood the details, but they claim the same is true if you go to QCD. So yes, this would be a contradiction to what some of the lattice groups say.
Mm-hmm. So as I understand, there are 2 issues here. One, whether you can fit with a power law, as in your, and the second, whether you can distinguish beta delta for Z2, which is about what, 2/3, from beta delta for O4, which is maybe 3/5 or something.
Yeah, exactly.
Right. So, and this MEV is where that distinction can be made, or where you could see the power law already.
Yeah, so I would say in this case, the crucial thing is that we need to be able to make the distinction. If I want to,
okay,
if you want a first principles answer to the question, right, you have to be able to calculate it. And,
all right.
And then, you know, it also depends very much how do you extract these things. This is very dependent on the procedure, and you can, so for example, few people, including us, as I have shown you, are able to get on. You have to get your quark mass is so small to be in the leading order scaling regime is practically impossible. The same was true for our work, but our situation is different because I'm looking for this tri-critical scaling. I'm not trying to distinguish anything, and that tri-critical point was guaranteed in our approach. That's the difference. And in practice, many people then play with subleading terms, or they take a constant. And if you're fitting, I mean, the fit always eats everything that doesn't match. It's very difficult to, so I would say it's not terribly constrained as at the stage where it is, simply because the quark mass is, or you can say it's an accuracy question. You would need enormously high accuracy in the small quark mass region if you really want to say something about scaling. That's going to be really hard.
Yeah. All right. I want to point out that there are some comments that Rob made in the chat with references. So if somebody is interested, look in the chat and don't miss that. I just have one other small comment. If there are no other questions, since we are almost out of time, can I just say that when you say that the mean field exponents are appropriate for the tri-critical point, what comes to mind is that it is upper critical dimension, and therefore there are log corrections to the mean field scaling. Have you considered the importance of those?
No, for the same reason. If I have a log correction, you know, have my accuracy is no way there. So I'm not in a position to talk about log corrections at all. Okay, this is what let me show the scaling here. You see, we are barely in the leading order region. Okay, so here is one example with 3 points. And the only reason I think it is okay, so what I do is a Taylor expansion in the scaling field. That is not a scaling law. So I'm just checking what is my natural expansion variable, essentially. And then, so here we are also subleading, but here is the new one. Okay, this was this makes me very happy. Here I have a 4th point, and now I have 3 on a straight line. But whether this is a subleading power correction or a log correction, there's no way. I mean, that's
yeah, I thought so. Yeah, just want to make sure.
Yeah, and I think this, by the way, I think this is where one can have all kinds of questions, but I think this is where FRG is really useful. I mean, if there is something they can do, that's it, right?
Yeah, to go to very, very small AM, right?
So in fact, in this new paper, they vary the pion mass over 4 decades, and of course they do this in the small direction. But that's really what does the condensed matter people do. You plot this, you have a log plot, and you vary over 3-4 orders of magnitude, and then you can claim you can see scaling, and that they say you see only once you're below whatever it was, 5 or 7 or so MeV.
Can you remind us, so what would be the conclusion from FRG about the order of the transition for 3 massless flavors?
They don't have the 3 yet. So the FRG work is doing somehow what we discussed first. So they are starting at the physical point and then going to the limit here. They have not done the 3 yet, but this is discussed. So these are all our neighbors, right? And now that Christian Fischer, this is what I mentioned here. So this, by the way, of course, doesn't have the lattice chiral symmetry problem. But this has truncations of Dyson-Schwinger equations. So this is also interesting what they do there. But so now I hear that I just talked to Fabian Rennecke yesterday, and he said they are going to look at the 3 flavor situation also. But this is not done yet.
That would be.
They look at it with FRG, and I think this is very good.
Yeah, if you can treat anomaly correctly, then that may help resolve this. Yeah. All right. So I think we are at the end of our time. I wish to thank the speaker for this very interesting talk, and I want to thank the audience for interesting questions and discussion. And I will pass the control to, oh yeah, hold on, Derek wants to say, oh no, Derek is uploading. Yeah, so am I.